Okay, so now we're gonna go through the same exact example. Um, I wanted to show you by hand to fully explain everything that we are actually doing because we're gonna have the calculator do the work for us to calculate the p-value. You just need to get all the information. Now, when it comes for the test, you guys are gonna have to do hypothesis testing. You're gonna have little lines like I'm gonna write the null hypothesis with the colon, give you a line to write your answer. I'm going to do the same thing. Alpha equals, same thing. Right tail, two tail, left tail. You're going to have to circle one option, okay? P-value, you're going to have a line right here to write the p-value. And you're going to have some space to write, you're going to circle your decision. I'm going to have reject, do not reject. You're going to properly circle it and say why. And all you do is say, like, p-value is less than or equal to alpha value, one of the two. But then you're going to have some lines to write your conclusion, all right? But to get your p-value, I'm going to show you how to do it in the calculator now. Now, you just need your data that we have here. Pull it off from the problem. Like I said, you still have to do all of this. Now, if you go to stat, just hit your stat button and go over to tests. It's the very first option. It says z-test, okay? If you look right below it, it says t-test. That is going to be for the next section when we do not know the population standard deviation. We know the sample standard deviation. And then in the section after that, one proportion z-test. Okay, that's for when we have proportions. So now all these are pretty much the same. Like it's all the same idea. The only difference is what kind of data do you have? So what type of test are you doing? I go to z-test. Now, you could put in raw data. Like if I go here, you could put in raw data, and it asks you for what list is the data in, what is the population standard deviation, and so forth. But we're gonna go to statistics. We know what the statistics are. Now, you see it shows a mu naught. Okay, mu naught. That's our the number we are using in our hypotheses. So I'm going to put 15. 15 right there. And then it also asks us, what is our population standard deviation? Well, in this case, it's 1.5. What is our sample mean? 17. And what is our sample size? Sample mean and sample size. So 17 and 30. Now, we didn't put in our alpha value. It's because the calculator doesn't care what the alpha value is to do this calculation. It's going to spit out the p-value for us, and we ourselves are going to take the p-value, alpha value, and compare them. So now, if you look at the bottom, you are telling the calculator what test are you doing. So the not equal to sign is a two-tail test. This next one, since the arrow is pointing to the left, like if you look at the inequality sign and we were to make an arrow out of it, it's pointing to the left, so that would be a left tail test, but we're doing a right tail test here. So we're going to hit that one, and now all we have to do is go to calculate. And it'll give you your answer. If you notice right here, it says P 41, and then at the very end, times 10 to the negative 13. That was the same exact p-value that we got when we did it by hand. So 1.41 times 10 to the negative 13. So that was a lot faster. Doesn't require us to use normal CDF and whatnot. If you notice, it also has a z-value. That is the z-score associated with this sample mean and this population mean. Okay? You could find the z-score. The z-score is equal to x bar minus mu divided by sigma divided by square root of n. We've seen this formula before in chapter 7. Okay? It's the same exact formula that we used then because we were using the central limit theorem. Same formula now. The other method that we're not going to go through is called the test statistic method. This would be our test statistic, but we don't need to calculate that, so you don't need to worry about that number on the calculator. But now, since we have let's see, p-value is less than our alpha value, this number is less than our alpha value, we come up with the same conclusion. Reject H naught. No surprise there. It should come out to be the same conclusion. So from now on, in the next example and in the other two sections, we are just going to do this on the calculator. I'm not going to go through and use normal CDF and whatnot to find these. One interesting feature for this calculator is the draw feature. You could draw the area that it's calculating. Now this one might not be that good because it's a really tiny area. Oh, I have another function plugged into there. Give me a second. Yeah, so it shows the normal curve, and if you look way over here, I mean, it's barely shaded, but that's because we have a really tiny probability. So let's check out the next example and see if we could get a better area shaded. So a lot of these hypothesis tests get done, especially for like quality control in businesses. This would be a good example of this. Let's see, it says a particular brand of tires claims that its deluxe tire averages at least 50,000 miles before it needs to be replaced, okay? So companies want to put out these claims for advertisement to compete with their competitors, okay? So they claim that, so here's our claim, that the average, particularly gets average mileage of at least 50,000. At least has an equal to sign because I could be at 50,000 or it could be greater than. At least 50,000 is the smallest. Okay, now it says from past studies of this tire, the standard deviation is known to be 8,000. So they told us the population standard deviation is 8,000 miles. Put units. A survey of owners of that tire design is conducted. Okay? They want to test whether their claim is correct or not. From 28 tires surveyed, n is equal to 28, the mean lifespan, so the average lifespan of all 28 of these people surveyed was, let's see, 46500 with a standard deviation, so they told you the standard deviation of 9,800 miles. Is the data highly inconsistent with the claim? Okay. Now, them telling us the sample standard deviation in this case is irrelevant, okay? So we don't even need this. So we could just get rid of it. This might have been useful if we didn't have past studies of the tire and know the population standard deviation, okay? Then we would do a t-test. That would be the next section. All right, so we have all the pieces of information that we need. We have our mean, this. We could plug all this in on the calculator, but let's start writing up our problem first, now that we have all this information. Not writing up the problem, writing up the solution. Wrong word. So, our null hypothesis. The null hypothesis had the equal to sign in it, and if you remember when we wrote our claim, it was at least 50,000, at least had the equal to sign there. So here's our claim. That means our alternative hypothesis must be less than 50,000. So here is step 1. Step 2, what level of significance? Using alpha is equal to 0.05, so they told us. Now we need to decide, is this a right tail, left tail, or two tail test? Okay, so if we're looking at this, you can see from the alternate hypothesis, this, if I were to draw an arrow onto this inequality sign, it points to the left. So this is a left tail test. All right, so now we have our sample data. Our mean here, our sample mean was 46,500. Our sample size here was 28. Now, before we crank out the numbers, let's think about this for a second. They're saying their tires last at least 50,000 miles. However, we have a sample mean of 46,000 miles. Are they correct? Are they just overstating their tires? Would this sample tell us that they're wrong? Or it just happens that it's 46,500. If we did more samples of 28, maybe they come out more than 50,000, okay? We could have just got a wacky sample. That's what we're going to find out right now when we calculate the p-value. So, p-value. To get your p-value, we're going to input this in on the calculator. So, let's see. We go to stat. We scroll over to the right to tests, and it's the very first option, z-test. Since we know the population standard deviation, see, for mu naught, I'm going to put 50,000. Then for, let's see, sigma, ooh, we didn't write that on here. Our population standard deviation was 8,000 miles, okay? So population standard deviation 8,000. X bar was 46,500, and our sample size is 28, and we're doing a left tail test, okay? So this is what it should look like. Let's see, just making sure that's everything correct. Yeah, this is what it should look like if you entered it on your calculator. Now you just go to calculate. Should end up with these numbers. See, we got a p-value of 0.0103. So our p-value and then our alpha value, which one is bigger? Well, alpha is 0.05. This is 0.01. So the alpha value is bigger than our p-value, or our p-value is smaller than our alpha value. Since our p-value is smaller than our alpha value, our decision here is to reject H naught. Okay? We're going to reject the null hypothesis. Okay? And that's where our claim was. Alright, so now that we know we are rejecting our null hypothesis, and our null hypothesis is our claim, we could write our conclusion. Let's go ahead and talk about what this p-value means real quick before I erase everything. Under the assumption that our mean population of the life of these tires is greater than or equal to 50,000, so we're going to make it as small as it can be. We're going to say it's equal to 50,000. If the average is actually 50,000, the probability that we got this sample mean is about 1%. Okay? So meaning it's a very small probability. So either one of two things happened. We made a type 1 error, because this is the maximum allowable error for maximum allowable probability for a type 1 error. So we either made a type 1 error when getting this, or we did find a sample, and if we collect more samples, they're going to come up with the same conclusion to reject the null hypothesis, meaning this is wrong, their claim is wrong, okay? So that's what the p-value is. The p-value is the probability that we actually get this sample mean under the assumption that this is our population mean, okay? Just going back to the central limit theorem. So let's go ahead and write our conclusion. there is enough, or you could say not enough, there is enough evidence, depends on how you want to write it, so there's enough evidence to reject the claim. You could write it a different way. There is not enough evidence to support the claim. Remember, this is where our claim was. How you want to write these, you always want to write them in terms of your claim. A good way of writing them is in terms of your claim. So here's our claim. There's enough evidence to reject the claim. Enough evidence at the alpha is equal to 0.05 level of significance to reject the claim that the average lifespan of the tires is at least 50,000 miles. Okay? So this would be the conclusion, what we found out based on our hypothesis test. Now, when we go over to the next section, 9.3, the only difference is we're going to be using t-test, and we don't know the population standard deviation, but everything else is the same. How we calculate the p-value, how we set up the null and alternative hypothesis, how we decide whether it's a right tail, two tail, or left tail test, everything's the same. Different calculator function. How we write the conclusion is the same. So the main important part here is deciding whether you're using a z-test or a t-test.